Okay, so the homework that we're going over, we're taking our slow steps towards linear functions. That's what it's all about. And in fact, all these are linear functions. They kind of haven't said it quite like that, but they talk about them as function rules. We know, because this is not the first time we've seen this stuff, that that's linear because it's kind of like mx plus b, right? Today, after we do this homework, then the first lesson in the next chapter is slope. So we're going to learn about that number right there, right? What is the m in mx plus b? So let's see, graph the function rule. I'm not going to do every one, but let's say I want to do the second one. What do we have to do to graph a function rule? And this does not have to be linear. It could be any old kind of function. A function rule it's an equation which is solved for y and has got some kind of an expression on the right. And it could be nonlinear, it could be linear. These happen to be linear. What do I need to do before I can graph this thing? So it's already solved for y. What do I need? What am I going to graph, actually? I mean, what's going to go wrong? How am I going to turn that into a graph? What do I need? Come on now. Where am I going to draw my line? How do I know where to draw the line? Say again? I need to get what? I needed some points, right? I need to know where the line is, and I get that from the points. So before I jump to having a graph here, I need a table of values, x and y, right? We need to come up with some points, so then we can connect those points with a line. That's how you graph them. Well, what do you get to make up? What do you choose when you make your table of values? You choose the x values, right? In a table of values, the x variable is the independent variable. It's the one on the other side that when you plug in, you can solve for y, right? So y depends on x because it's solved like it is. So we're going to pick x values here. And because we get to pick, and that's why I picked this one in particular, we should pick numbers that are convenient to the calculations we've got to do, right? What kind of numbers would be easier when we make our calculations? Even numbers, because you're multiplying times a half. It might make more sense to make them even numbers. And you could make them, you could pick any ones you want. 0 is always good. How about it just to be symmetric? I'm going to do -2, 0, and 2. Okay. If I plug in a -2 for x, what do I get as a y value? -1, right? If I plug in a 0 for x, what do I get for a y value? 0. And if I plug in a +2, I get 1. Right? By not picking 1 or 3 or odd numbers, I don't get y values that are fractions. I'd prefer not to have that. So remember, whenever you do the graph a function rule, make a table of values, pick some x values, calculate the y values, plot the points. Right? So this will be -2. Sorry. And I only need my grid like that, right? My grid lines. So -2, -1, 0, 0, 2, 1. So there's your points. Connect them with a line. Right. Make table of values. Right. I'm going to leave the other two for you. Did you have a question, Devin? On what? I gave you credit for it. Okay, these are identify domain and range, and then say whether it's a function. It says actually to make a mapping diagram, but if you can just say that one part, mapping diagrams really don't come into play very often with most of this stuff. How do you know what the domain and the range is? For example, on the number 1, the domain is the set of the x values. So if I'm going to use D for that, right? the domain is, and these curly brackets, that means this is a set of something, right? It's a set of the x values, 3, 5, 7, 8. 3, 5, 7, 8. Okay, what is the range? 6, 7, 7, 9. And generally, don't repeat, put them in order. So I just said 6, 7, and 9. I don't need 7 twice. It's already in the set. Is that a function? What is it you look for to see whether it's a function? Yeah, if there's, what doesn't repeat? Yeah, I mean, it's okay that the y values repeat. It's not okay if the x values repeat. So this is, right, no repeated x values. Right, therefore, function. Which one of these would not have been a function? Did you say number 4? Let's see. 0.3, 0.3, 0.4, 0.3, 0.5, right? So, not function. Again, at the very least, you should be writing down the domain and the range in order, no repeats. Say whether it's a function or not. Good? Use a vertical line test to say whether or not a graph is a function. Right? Now, if I look at this graph of points here, I could write down those values. Right? I mean, there's just 4 points on the graph, so that's easy enough to see. Right? What is this point? -4, 3. How about this point? -2, -1. How about that point? 1, 2. And this one? 3, -2. And clearly looking at the points, it's a function. It didn't repeat any of the x values, right? The problem with a continuous line, which is the graph, how many points make up a continuous line like that? Infinitely many points, right? If you zoom in, there's still more detail that you don't see. And then you can keep zooming in and zooming in. If you could pick the 2 points you think are the closest on the graph, there's still infinitely many points in between those two, right? It goes on forever. So there's no way for us to write down a bunch of values like that and check the x values to see whether they repeat. Instead, you're going to look at a vertical line. Try to imagine, could you draw a vertical line anywhere in there and have it cross that graph in more than one spot? I mean, in just what we're looking at there, let me do this blue. Here's a vertical line. I mean, are you talking about these here? No, don't connect the dots. It's just those points. I mean, look at this here. Is there any place I could move this line? Oh, I thought I'd be able to do that. And it won't let me do it anyways. But anywhere we could imagine that blue line going to where it would cross in more than one spot? And the answer is no. I mean, all you can do is imagine. It's usually pretty clear when it's not. You know, if it's something like that, I mean, you can definitely see a vertical line would have crossed in 2 places. Right? But in something like that, you just have to say, I can't see it, so this is a function. Well, again, here's the 4 points. Did they repeat any x values? No. I mean, every one of these is on its own vertical line, right there, 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 right? So, no, there's only one value on each vertical line. So that is a function. This is a function. Okay, then we got into what's called the function notation, right? The function notation is usually written like f of x equals but you can use other letters than F. And in this problem, which is like the one we did in class, the function was W of X, which is the number of words you can type, is 60 times X, where X is the number of minutes. Right? How can you find how many words you could type in 9 minutes, given a function like that? Yeah, it's like saying find W of 9, right? And how do you find W of 9? You plug in X equals 9, right? So you're going to say 60 times 9, which is 540, right? That's kind of a multiplication table thing, right? 6 times 9 is 54, add a 0. Sound travels 343 meters per second, right? The function d of t equals 343t gives the distance in meters that sound travels in t seconds. How far does it travel in 8 seconds? Okay, plug 8 in for t. That's like saying find d of 8, which is 343 times 8. Now that we probably need to do off to the side, right? 24. 8 times 4 is 32, plus 2 is 34. 8 times 3 is 24, plus 3 is 27. 2, 7, 4, 4. Does anybody know the rule of thumb for if you hear a thunder, how do you know how far away is? You count the second. Yeah, if you see you see a lightning, and then you wait to hear the thunder. What's the rule of thumb for? Okay, and how many seconds is 1 mile? It's 5. It's about 5, and it's based on this thing. You know, it's a comparison between the distance of, or the speed of sound and the speed of light. You get it much, instantaneously from the light, and then you wait that number of seconds when it's traveling that speed, and you see. Okay, 5 times 3. I mean, we ought to be able to do that. Let's see. If I plugged in 5 seconds, I would get 5 times 343, which is 1,500. 5 times 40 is, what is that? 5 times 343 is 5 times 343, 15. 5 times 4 is 20, 21. 5 times 2 is 15, 17, 15. 17, 15. Now, what is the unit of our answer here, given what they said in the problem? Sound travels 343 meters. So that's actually in meters. How can I convert? Because right now, that doesn't tell me anything. I just said it travels about 1 mile in 5 seconds. Okay, in 5 seconds, that's 1,715 meters. Any kind of a rough estimate of how many feet in a meter? It's kind of like 3, right? A yard and a meter are pretty close to the same. So I always think of it, a yard is 3 feet. If you multiply this by 3, you're going to get 5,145. And how many feet are there in a mile? 5,270 or something like that, right? So yeah, you can see where that's the reason why when you see the lightning and you count to 5 seconds, it's a pretty good telling you about how many miles away it is, right? If it goes to, usually I find that if it's within a mile, you're going to hear the thunder. If you got to count to 10 seconds, which means 2 miles away, usually you're going to hear the thunder. When it gets to be like you're counting up at 15, 16, you're probably not going to hear anything. Maybe it was too far away. No. It's when the lightning flashes. That's when you start to count, right? So, because the thunder is the sound of the lightning. Right. You count until you hear the thunder, and that's going to tell you about how far away it is. Now, let's say that we're in here, and we see a flash outside the window, right? And we count 1,000. Usually that's how the old-fashioned way of counting, to make sure you don't count too fast. 1,001, 1,002, 1,003, 1,000. We get up to 10 and we hear boom, And then a few seconds later, maybe a minute later, we get another flash. And this time we count to 5. And what does that tell you about the thunderstorm? It's coming at you, really quickly, So then you're waiting for the next one, and you're pretty sure it's going to be right on top of you. We had that happen once out here. We had a flash of light out there, and because I'm just used to doing this, I started counting to myself, and the students are saying, "What are you doing?" And I said, "Well, you count to 5, and that's going to tell you how many miles away the thing is." And they didn't know that, so it was kind of new. You guys seem to know a little better. 5 seconds. So they thought that was kind of interesting. And then within a few minutes, we had one that was like right overhead. I mean, it was just like all at once, a flash and a bang, and it was really loud out here. You can imagine in these trailers, like you get something right overhead. I think it like hit some trees just over there, really. But that was something. Okay, and so now we're getting into the lesson part, right? And the lesson part, I have to say that this lesson, which is about something that you know about, which is called slope. What is the slope when you're talking about a line? What does the slope describe? Yeah, I mean, if you're looking at a line on a graph, it's the tilt of the line, right? It's the tilt, right? Is it going up from left to right? Is it going down from left to right? But in terms of math and science kind of stuff, it's actually, and this section I think is titled Rate of Change, right? It's how much is the y value changing for every little bit that the x value is changing. In this here, it says, the table shows the distance a band marches over time. Is the rate of change in distance with respect to time constant? So they're saying, how much is this value changing from here to here, like 260 to 520, what's the difference? What's 520 minus 260? It's 260. 520 minus 260 is 260. So this change is 260. And then you can do the same thing. What's 780 minus 520? 260. And what's 1,040 minus 780, 260, right? Now notice that the x values were also changing in steady increments, right? It went 1, 2, 3, 4. So the rate of change here is that it's 260 feet for every minute, right? The distance that the band is traveling. Now, when this is a constant, you're dealing with a linear function, right? It's something that has a graph that looks like that. Now, do lines that are curved have slopes? Yes. They do, but they're not constant. They change, right? A line, a function, let's say a parabola, right? Which you've dealt with parabolas before. I mean, that has, every point on that line has a slope, right? But it's changing. That's the first part of what you study when you get to calculus, is to come up with a function that will describe the slope of that line, the rate of change for every point on the line. But right now, all we're interested in is slopes that don't change, and that means linear functions. Okay. So if I graphed the one on the previous slide here, you can see these are the points. And you could see for every one, you go one to the right, in 1 minute, and it looks like you're going 260 feet more. They're kind of trying to get around explaining this concept without just going right to the formula, which we all know that's coming, right? So that's the idea graphically. What do we mean by the rate of change? Now, slope, if you're looking at that same graph, right, slope is described as the vertical change, the up and down, divided by the horizontal change, left and right, which they also call the rise over the run. You've heard those before, right? Rise over the run. Okay. So if you look at this problem right here, and notice on this graph that on this straight line, there are 2 points that are highlighted, and they've given us the coordinates of those points. But you can kind of see what the change is just by looking at the graph. Like if I go from this point to this point, what is my vertical change? It's positive 2, right? And if I go from this point to this point, what is the horizontal change? It's 3. So what would you say is the slope? 2 over 3, right? So we're going to say m equals 2/3. Okay. How about this one? To go from this point to this point, what is the vertical change? It's down. So when you're going down, it's negative. So that's -4. And what is the horizontal change? +5. So you're going to say that that is m equals -4 over 5. Okay, what's the slope of these two? Okay, from this point to this point, what is the vertical change? Right? This is 2. This is 1, 2, 3, 4, 5. So the slope is 2 over 5. Okay, do that one. Okay, so it's down 2, right 6. But actually, that could be simplified. It could be 1 over 3. So it could be -1/3. Which, if you look at this graph, notice how they picked these 2 points. You could have picked that point right there, right? And then it would be down 1, right 3, which brings up a point. Does it matter which the points are that you choose for the value of the slope? No, any 2 points will do. Any 2 points. Now, this I'm showing you because most of the time when you have to look at these graphs, they don't have 2 points, highlighted and the coordinates. Usually, you're just going to look for some place where it looks like the line is crossing the intersection of the grid lines so that the calculation's easier. I mean, again, you could pick any 2 points. You could pick them right in the middle like there and there, but now you're estimating where is it. So it's better if you just look for a place where it's crossing the intersection of grid lines. It keeps everything in whole numbers. Like how about there and there? Okay, what would be the slope if you use those 2 points? Up 3, right 1, 3 over 1, 3. Now the formula, which we kind of use implicitly when we do that on the graph, but the formula is, if one of the points is labeled x1, y1, and the other one is x2, y2, then remember that the x-coordinate is a horizontal coordinate, right? It's telling you where to go left and right. The y-coordinate is a vertical coordinate. It's telling you where to go up and down. So you definitely want the up and down, the rise in the numerator, and the left and right in the denominator, right? Rise over run. If there's a common mistake is flipping that. Make sure the y's are in the numerator, x's in the denominator. Or another way to do it, what if you had this problem, if you know how to plot the points, so you feel comfortable getting it from a graph, then graph them, right? Just graph them. I'm sure you probably make less mistakes putting the y, changing y in the numerator if you did that. But if you don't, I got to consider one of these points to be x1, y1, and the other is x2, y2. Does it matter which one I pick? It doesn't. You just got to be consistent, right? So if I say this one will be my x1, y1, and this one is my x2, y2, then I'm going to plug into that formula. M for slope equals, the y2 is -2, the y1 is 0. -2 minus 0. Right? 3 minus -1. Right? Simplify. -2 minus 0. What is 3 minus -1? It's like 3 plus 1 is 4. Okay, can you simplify that? It is -1/2. Okay, how about this one? Try to do this in your head or on a piece of paper, whatever. What's the slope between those 2 points? Wait. Andre's going to get for us. Devin, you working? Not you, but it goes. I guess I should ask you too. Are you working? School's so hard, isn't it? Who's got an answer besides Pat? Dwayne. -3/4. What'd you say? -4/3. Right? It's got to be this one. -1 minus 3 is -4, right? And then 4 minus 1 is 3. So m equals -4/3. You get it? Okay. Now, I think the last horizontal and vertical lines have kind of special slopes, and we make a lot of mistakes with these. We never quite learn how it is to refer to a horizontal line or a vertical line. And we get confused when, for example, one of these has a slope of 0, right? The other one has a slope which is undefined. Okay, which one would have a slope of 0? So if you just plug into the formula, right? In this one here, if I plug into the formula, I'm going to get 2 minus 2 in the numerator and 2 minus -3 in the denominator, which is 0/5. Okay, what is the number equal? 0/5. 0, right? A fraction that has a 0 in the numerator equals 0, right? Now, on a vertical line, right, when I do this math, I'm going to get 1 minus -2 divided by -2 minus -2, which is 3/0. Okay, what does a fraction equal when it has a 0 in the denominator? Undefined. That's the one that's undefined. I mean, I always think of slope is the tilt of the line, you know, whether it's increasing or decreasing as the line goes from left to right. But the vertical line doesn't go from left to right, right? It's only in one place. So there is no left or right to it. That's why it's undefined. So this is the one that's undefined. So if I look at this line right here, those 2 points are highlighted. What would be the y-coordinate for this point? Oh, sorry. What am I looking at here? Oh, yeah. No. What is the x-coordinate for this point? -2. What is the x-coordinate for this point? The x-coordinate. And this point? This point? -2. And this point? What is the x-coordinate for every point on that line? That's why the equation for that line, x equals -2, right? Same way here. What is the y-coordinate for, we know what it is for these 2 points, but what is it for all these other points on the line? It's always 2. So when you write the equation for a horizontal line, it's y equals a constant, because that describes every point on that line. It's described by y equals 2. Okay. That's a little bit ahead of where we're going, but so which one of these is going to have a slope which is undefined? The other one is 0. Which one is undefined? The A? Why? Right? Because the x2 minus x1 in the denominator is 0, right? This is 0, undefined. And how about this one? right? That's -3 minus -3 in the numerator, right? And in the denominator, 5 minus -1 is 6, which is good. That's 0. Don't confuse 0 as a number for something that's undefined. 0 is a number, right? It's in between positive and -0. And that is the way I like to think about this. You know, positive slopes go up, negative slopes go down, right? Right in between positive and negative, right, is 0. That's 0 slope. This is the one that's undefined. So, horizontal and vertical. I mean, I've had times in the past, I tell you, the kids don't understand the concepts of horizontal and vertical very well, to the point where you start to wonder whether they don't really even understand what the word horizontal means, you know, or like maybe the word horizon, because what's the horizon? You know, it's the, you know, the earth, as you're looking at the side of the earth like that, that's the horizon. So that should remind you of horizontal, right? But I mean, I remember in an Algebra 2 class years ago, I just said, with your hand, show me what is a vertical line. And I'm telling you that half of them were doing this, and half of them were doing that. And now, you know, when there's only a 50-50 chance of getting it right, what does it tell you when 50% is doing this and 50% is doing that? Guessing. Probably just about everybody was guessing. They didn't know. So, okay, the homework is going to be on that page, 139, 1 to 15. So write that down, and then we're going to take a quiz.